today that we can welcome Andrew Baker from Stanford University to our webinar. And he's going to give a talk about difference and differences in 2020. Andrew, the floor is yours.
All right. So is my screen being shared right now or no?
No.
Here, let me see.
Oh.
Okay, now can you guys see it? Okay, is it up now or no? Yeah. Okay. All right. So, like we said earlier, this is a talk on some work that I'm doing about difference and differences. But more than anything, I have a paper coming out, kind of looking at this in my specific field setting, which is accounting, finance, law. And so what I'm really trying to do is kind of take what really smart econometricians have done on this and translate it into language that dumber people like myself and my co-authors can understand. And so what I'm really trying to get out of this is kind of distilling like what I think is important about this new literature that's come out about some flaws with difference and difference when you have staggered treatment timing. So I really would appreciate it if like anything is unclear, like it actually would be really helpful to me if like you guys have questions to like just raise your hand and clarify. For a brief outline of the talk, I'm just going to kind of very briefly go over difference and difference. I'm sure that a lot of you kind of know what this research design is, but just to kind of get to the primitives of it and how it developed. What are the problems with the kind of staggered difference and difference design that's very popular now? I'd say it's probably most studies across econ disciplines. I'm going to use some just like very simple simulation results because for me at least it's like kind of the easiest way to see like what this issue is and how it pops up and when it's kind of when it is a problem and when it might not be. I'm going to present some alternative methods that have come out, some recent papers, including some people that I'm working on stuff with. And then if we have time, I'll get to a brief application of a paper and kind of show how you should apply these methods to different data sets and whether or not it matters or not. All right, so kind of very briefly, let's go over like what is difference and differences. I mean, usually the example I think of, because it was the paper that kind of started to popularize this again, was the Card-Krueger minimum wage paper, right? So big kind of topic in labor for a long time. Generally, most people felt like minimum wages would kind of hit employment rates, right? That you have this trade-off between having to pay people more, then they're going to hire less. But there wasn't that much actual empirical evidence. So Card-Krueger did a study where they looked at one minimum wage change between New Jersey and Pennsylvania. They looked at fast food employment between the two states. So here there's kind of 2 units, 2 time periods, right? So we have 2 states, New Jersey and Pennsylvania, before and after. I believe it was New Jersey passed a law raising the minimum wage. Pretty much you have 1 unit, which is a treated unit. This receives a treatment in the 2nd period. And there's a control unit that never gets treated, right? So this is kind of like the very simple way you could think about an RCT. You could think about anything, right? You have 1 unit that never gets whatever the shock is or whatever the treatment is. And then you have a control unit. And so this is the way I kind of think about it, right? Over time here, red, right is the control unit. So, there could be some pre-existing time trends, things change, placebo effects, or just general time dynamics, right? And then we have this kind of blue line, which is the change in the outcome variable for the treated unit. And what we want to do is say, what percentage of this change in the treatment unit can't be just explained by the change in the control unit. And we're going to then ascribe that to some treatment effect from whatever it is that we're studying. All right, so kind of building upon everyone's favorite, reference textbook, Angress and Pischke. We can think of these as like what they call kind of simple 2x2 difference and differences, right? Which is kind of what I just showed you. So you have 2 units, 2 time periods. And you can think about this as a fixed effects estimator, right? So if we put this in the kind of potential outcomes framework, we can have like y IT1. So I is going to be whatever the unit is. T is going to be the time period. And then 1 is just kind of to signify like what is the value of this dependent variable if that unit receives treatment in that period, okay? And then what would be the same counterfactual value for that outcome variable if it didn't receive treatment, right? So these 2 things obviously cannot both be seen in the world because you either get a treatment or you don't, right? So this is a whole kind of potential outcomes sideshow trick that you do where you can kind of write things in terms of expectation functions and kind of get at the treatment center, right? So this is what I was saying. So we think that there's some expectation value for the outcome variable when it doesn't receive treatment. And we think that this is some function of a specific kind of attribute of the unit, a specific attribute of that time period. And then we think that there's a treatment effect if this unit receives treatment, right? And so the goal of a difference in difference is to just get an unbiased estimate of this delta term here, right? This treatment effect. And so the way I kind of think about this is just to think about it as like a simple system of equations, right? From kind of doing algebra back in like undergrad econ, right? So assume again, we have two units, the treatment unit and a control unit, right? So here, what this is saying is that for the control unit, right, it's going to be a function of these kind of fixed effects for the control unit. So Pennsylvania has some underlying rate of unemployment or underemployment, right? And New Jersey and Pennsylvania might differ for systematic reasons that we just maybe don't care about or we're not modeling, right? And this is kind of economy. We can talk about this, why economics is obsessed with fixed effects estimators, but that's a different equation or a different discussion. So right, in the first period, which is the second period, right? Essentially, there are these time components, right? And so you can get the change over time if you subtract these two things, right? The fixed component for the state or the unit or the firm or whatever it is you're studying, that drops out, sorry. And you can do the same thing for the treated unit, right? And all this is to show is that you can get an estimate of this unbiased average, hopefully unbiased treatment effect average by just taking the double differences, right? So if you subtract out the time component first, actually, sorry. So this is if you subtract T1 minus T0, right? Then the firm components from each of these will fall out. And then if you subtract them from each other, right? The only thing that'll kind of still be here in this equation is this delta term, right? And so this is kind of how it looks in the data, right? I have this little GIF if it works, right? So you first kind of remove the differences that are just fundamental to the two states. And then those two differences over time that can't be explained, that's going to be the treatment effect, right? It's a very simple estimator, right? I just want to kind of, so we're all on the same page about like what is difference and difference, because you read these in papers now and people don't kind of tie it still, I feel like, to like what the underlying estimator is, but all it is a difference of conditional means. And so then the only point is, you know, what we just saw, I showed you can calculate that delta term by just subtracting, right? It's called the difference in differences because you subtract the mean two times. You can also just do that with the regression framework, right? Which is what we all do, right? People don't actually calculate these differences in means because if you just throw in kind of indicators for which of the firms receives treatment, which of the time periods is post-treatment, right? And then the interaction of those two things, the coefficient on that interaction is mathematically equivalent to that double difference that we just did, right? And this just shows kind of like what these kind of coefficients equal out to, and it shows that, you know, again, this is all from Engers and Pischke, like, don't need to get into it, but this is how we went from kind of a difference in difference of calculating difference to means to people realizing, hey, it'd be easier if I just kind of threw this into Stata, did a regression. All right, and so now we have, you know, what we call regression difference in differences, okay? And so the advantages of this over kind of the mean approach is that you get these nice estimates of the standard error that comes straight out of the regression framework, right? So if you kind of throw your matrix into Stata or R, whatever you use, and you estimate it, you not only get that treatment effect average delta, but you get some estimate of the asymptotic standard errors, right? And so I call this the kind of like workhorse model because it's just in so many papers now, at least in the disciplines that I read. And so what Engers and Pischke say is that, you know, it's also easy to add additional units or periods to the setup, and it's also easy to add additional covariates, right? So what we all kind of use is this kind of two-way fixed effects estimator, right? So we regress our outcome variable on both, you know, unit fixed effects, time fixed effects, and then this treatment indicator that turns on for treated units after they receive treatment. Okay, so this is just a different way of doing the same regression that I showed you here, except with the fixed effects, you know, the treatment and the post variable are subsumed by the fixed effects, and so all you're focusing on is the coefficient on the indicator variable, right? And so then you can add in a matrix of time varying covariates, although I will say we all do this, but the actual theory behind the time varying covariates, you know, you're putting a lot of assumptions on your difference in difference is just the only thing I'll say when you throw in a bunch of time varying covariates and 4 levels of fixed effects and all these things. But But essentially, this is the kind of regression framework that we're all kind of working in. All right, so what have we found out in like the last couple of years? You know, that's just kind of leading up to where difference in difference is, why we all use it in all of our papers. It's kind of easy to explain. It's quite easy to implement. But there's now a kind of longish literature, showing that when you use the two-way fixed effects estimator that I just explained, but the treatment timing is staggered, right? So if you think about it, the Pennsylvania example, you know, there's one period of treatment. But frequently, if you think about like the paper that if we have time, that I'll get to today, looks at the staggered rollout of medical marijuana laws within the United States. And so what you have is, instead of one period where this treatment turns on, you'll have multiple, right? And so you could think about it like an advantage of this is, you know, the identifying assumption of difference in differences is that the treatment units and the control units would have followed the same path had there not been a treatment, right? Those trends would have been the same. And therefore, we can ascribe any of these differences to whatever this treatment effect is. It can be harder to do that if you only have one treatment, right? So say you have half of your states adopt something in 1 year and half don't. You know, you're always going to have reviewers or commenters in your talk say, well, maybe there was something else happening at that time. The allure of the staggered announcement is you need something to consistently be kind of occurring at that same time that explains these counterfactuals. But mathematically, it turns out that we get these really weird estimators when we do this. So, you know, without kind of really digging into this estimator too much, all I'll say is that the two-way fixed effects estimator, which we just called the delta DD, with staggered treatment timings, what we figured out is that it's a weighted average of many different treatment effects. But we don't know very much, or we did not know very much, about how it measures the treatment effect when the treatment timing varies. In particular, like what means is it comparing across groups, and why do specification changes change the estimates? It turns out these weights can often be negative and very non-intuitive. So it doesn't just give you the same simple estimate that, you know, the previous kind of very simple difference in difference estimator did. Okay, so before I move on, does anybody have any questions? I realize I'm just kind of running through this. I haven't seen if there are any comments. Is everybody good? All right.
So just to sum up. So basically, the idea is if you are in the only case, the Anderson-Pichte case is the only case is the Carden-Kruger, basically, because that's the only case that I know, like famous one, where you actually have the 2 periods and everybody gets the treatment after the introduction of the law. So that's the only probably case where the different diff that we study in books can actually be applied. All the other cases needs to be some thinking. That's more or less the bottom line, right?
So yeah, I mean, one thing I'll say is that when we say like the 2 by 2, I was confused by this a lot too. It doesn't necessarily mean that there could only be 2 states. You could have something, say there's 50 states and 25 states are treated and 25 aren't. And that's still technically considered a 2 by 2, because what you do is you just swipe out those means from the different states. So you'll put the state fixed effects in, and those will actually, I'll show you in the simulation, those will actually still be okay. And I do think that there are still, again, off the top of my head, I can't think of any, but there are, I think, a lot of papers that have that kind of setup where you still only have a pre and a post of one time in which the treatment turns on. But I agree with you. It's rare that you have something like, you know, a simple, like actually only 2 time periods and 2 units. Because in that case, I mean, you can't even include any covariates, right? It's exactly identified. So I agree with you. It's rare to see something like that that's kind of low. And I was talking to a friend yesterday who said he's trying to get a paper published where there's not staggered timing. And he said that he gets a lot of pushback for the fact that there isn't staggered timing. So I think most papers that use difference in difference use the staggered nature of the timing.
Cool.
Yeah. All right. So I actually think that this derivation from this paper by Andrew Goodman-Bacon is the kind of cleanest way of explaining like what the issue is here. So I'm just going to kind of walk through these plots from his paper that shows what the issue is. It's just a nice graphical intuition. So assume that this is the way your data looks, okay? And so you have 3 groups here. This green line is going to be what we call never treated units, right? And so there's just assume that like assume this is like gross income or something over time, right? That there's some naturally increasing nature to the data. So even the untreated units are kind of gradually increasing over time. And then assume that we have just 2 treated units, but these could be groups, right? Assume there's 50 states and, you know, a third of them are treated early, a third of them are treated late, and a third of them are never treated, okay? So this is, you know, I think the simplest staggered design that you could think of, okay? And so what we'll have is we have these 3 time periods. So the time period when no one's treated, the time period when just the first group is treated, and then the time period when both the treatment groups are treated and the untreated group is obviously still untreated. And so what the paper shows, which I think is just a really nice result, is that this is equivalent to 4 different 2x2 differences, okay? So what you have is you have the early group against the untreated group, right? Until so the early group versus the untreated groups. So these are the 2 top plots. And so this will be the full set of the data, okay? Then what you have is you have the early group versus the late treated group. So this is only identified until before the late treated group is treated. And then you have the early treated group versus the late treated group, right? So this is the second half again. So we have to just kind of look at like this was what the plot looked like in total. So, you know, you have the full thing for the untreateds, but then you have just like, it's only a segment of the data. You need at least one of these things to not have the treatment assignment change over that range, while it does change for another unit. It's the important point. Okay, and what he kind of shows in that paper is that the overall two-way fixed effects estimate that you get is just a weighted average of those 4 underlying treatment effects. And that's true in any of these differences that we run here. It weights these different comparisons and it creates one weighted estimate. The weights are a function of the size of the subsample, the relative size of the treatment and the control units, and the timing within the subsample. What's also really important and what generates the bias that I'm going to get into is that the already treated units, they act as controls even though they're treated, right? So I think a lot of people don't realize that when you do this, that after a unit's treated, right? So in this plot right here, red gets treated early, but in this regression right here, it's actually the control for the blue unit, right? And so if there's any kind of time varying nature to the treatment effects, like it doesn't happen in one period, this estimate here is going to be biased. It's going to be biased downwards. Okay, and so, you know, given a couple of things that, you know, come out of this that maybe aren't ideal is that given the weighting function, panel length alone can change the difference in difference estimate quite substantially, even when each of these treatment effects doesn't change, right? Because it changes all the weights that go into this. So sometimes I see papers where, you know, we're looking at treatments that happened in the late 80s and people would just use data through 2010, right? And that'll actually change all the estimates underneath here because it's just giving different weights to things, even though treatment all happened 10, 15 years prior. In addition, groups treated closer to the middle of the panel, they're going to receive higher weights than those treated earlier or later. I don't know if that's ideal or not. I don't think it is, to be honest. And now this doesn't happen if you use kind of like an event study approach. But, you know, if you have units that are treated really early, they're going to receive less weight than something that's treated like directly in the middle of your panel. And the reason for that is that the variance of that treatment indicator variable is highest. You know, so any variable that only takes the observations of 0 and 1 has a highest variance when it's half turned on and half turned off, right? And so that's how that happens because OLS weights everything by variance. All right, so I'm going to run through just a quick simulation exercise that, for me at least, explains this issue the easiest. Does anybody have any other questions before I kind of run ahead with this? Everybody's good? Yeah, okay.
My question is regarding the type of treatment. So if the treatment is continuous, but still staggered, for example, cigarette taxes, right?
Yeah.
Does anything change or are we following the similar framework?
You know, I talked to some of the econometricians so some of them and I are a couple of the people, Andrew Goodman-Bacon, whose paper I went through, and Pedro Santana, who's one of these approaches, I think have started to kind of look at that a little bit more. I would just say, you know, I've done studies with treatment assignment that's not discrete, and in that point, it's actually quite hard to understand what the difference in difference really is, right? So like I explained to you before, the Pennsylvania and New Jersey comparison of means, when the treatment assignment is actually continuous, I think a lot of that literature is now developing, trying to kind of figure out what that is. I don't see a reason why this same issue would not also kind of apply, but it's just hard, right? Because these things are constantly changing. Like cigarette taxes is constantly going up and going down. And so it's hard to know what the bias would be there because they're constantly turning on and turning off. So that's all I'll say is that I don't have a great intuition in terms of how these biases per se map into that approach. But it's also not quite clear what those comparisons of means are in a difference of difference when you have a treatment variable that's continuous. So I think it's not a very satisfying answer, but my guess would be that some of these issues apply, but some of the theory behind the difference of difference with the continuous variable are not super fleshed out, is my read.
Thank you so much.
You're welcome. I think I saw another hand pop up at some point.
I have a question, if I may.
Yeah, sure.
So you mentioned arranging the data as an event study.
Yeah.
Would that get over your problem?
So there's two issues with which I'll show you actually through the simulation exercise, but let me first address your question. So there's two issues with the bias that arises from this difference of difference. One is this issue that I talked about at the end, which is that you upweight things that are treated in the middle of the panel and you downweight things that are treated as the tails. The event study does solve that problem, right? Because now that treatment indicator is going to be, the variance is going to be the same for all of them, right? Because they're only turned on once. But it turns out, and this the paper by Sun and Abraham, that paper showed that even doing the event study approach does not solve the fact that you're comparing prior treated units to post-treated units, unless you saturate the fixed effects in a way that I'll show you, which is what their paper does. If you just still only use one set of indicator variables, leads and lags, you're still biasing. Those are going to be bias coefficients. So it solves one of the problems, but not the other one. The problem is that the real thing that really messes up the estimates, which I'll show you in a second, is not so much that weighting issue that I talked about. When people try to tell me like what's the big issue here, I try to kind of point out that weighting issue, it's unclear if you necessarily want to exactly weight things depending on when they're treated in the sample. And in my simulations and my experience doing this, that doesn't matter that much. What really can mess up the estimates is the fact that you're using prior treated units as controls for future treated units. And that is still going to be an issue with the event study approach.
But you don't have to do that.
What do you mean?
Have to use those previously treated units as controls.
You don't have to. I mean, so there's a few ways that I'll talk about to get around this. One is a stacking, but if you just kind of do I created indicator variables for pre and post, and I have units within my panel that were treated at different times, it will naturally use the pre-treated as controls for the post-treated, unless you're careful in structuring your data in a way that doesn't happen.
You could code it away, yeah.
Yeah, you can code it away, but from my experience, most people don't. And so I think a lot of this literature is just showing that you need to do that, and that it can matter a lot in some examples. But I agree with you. Like what I call the stacked regression approach is simply doing that, ensuring that prior treated units don't act as controls, but maintaining the same kind of linear functional form, same event study approach as the kind of Angerskine-Pischke model in the book. Yeah.
There are two raised hands. I think, Sylvia, you can go first.
Thank you, Andrew. I have one clarification question.
Yeah.
Can I think about this framework the same as kind of the standard warm paper of Kremer or like in general development paper where I have that all groups get treated in some sort of time?
Yeah.
So there is never a group that is never treated. Is the bias increasing in this case?
Yeah.
Or we are talking about the same?
Yeah, no, that's true. I mean, those are the ones. So I have a paper coming out soonish, hopefully, that I don't want to deal with, send the papers to the authors and everything. But my experience, that's where this issue really, really bites. And by bite, I don't mean like really stinks. I just mean like where the constraint really binds is that if everything is treated by the end of your panel, that's where I've found the estimates can like flip signs, actually. Like you're finding a positive effect and the actual effect's negative. That can happen in these cases quite easily, where there's having no units that are never treated. That really helps a lot here if you're going to do the standard approach. When you don't have any never treated units, that's when these things can really start swinging around a decent amount.
Nathan, you have a question?
Yeah, I just wanted to ask, so in the like graphs you showed for intuition, the effect of the treatment was only on the level. And what would happen to the bias if it affected the growth rate of whatever variable you were looking at?
Yeah.
Just because then all the
Yeah.
already treated units are growing more in improper controls.
Yeah, so that is when it, that's another thing. I'll show in the simulation exercise here, I'll show you, we have, I show three different ways. So this is kind of what you talked about, the level shift, where there's much less of an issue. When you have something where it's like a trend shift, that's when also it'll be much worse. Yeah, that's it's a good point. That the kind of Goodman and Bacon graph is kind of these discontinuous, and none of these issues are that bad in that case. But when it, I think it's rare to think that your treatment effect all occurs in one period and then stops. I mean, if you look at most event study plots, right, there's this kind of linear, kind of like log growth, right? Like it might take a few periods and then it kind of levels out. And so anytime that happens is when you're at the risk of this too. So that was a good point.
Okay, thanks.
All right, so let me walk through this simulation exercise. For those who are like me and don't always love just doing the algebra, I just find simulating data for this stuff to just be like a lot easier to see how it happens. So I work mostly in kind of corporate governance, corporate finance type work. So this simulation is based on like a data structure that's like that, but you could do this, I've done it, where I pretend it's states, it doesn't matter. Assume we're modeling some outcome variable Y. And here, assume I have a balanced panel of 36 years. So from 1980 to 2015, and assume I have 1,000 firms, right? So I'm in the US, I'm studying some firm level variable, okay? We assume that there's some time invariant unit effects. These are firm effects. And we have time varying year effects. And we assume that instead of these all being a constant, I just like there to be a little stochasticity here. So I draw these for each firm from like a normal distribution, mean zero, variance a half. Right. Firms are incorporated. So in the US, the law for corporations is based on the state in which you're incorporated. So assume that this is just they're located in one of 50 randomly drawn states. And then these states I randomly assign into 3 treatment groups. Okay. So some groups will be treated in 1989, some will be treated in 1998, and some will be treated in 2006. Okay. So just kind of equally spacing out 3 different treatment timing groups. I'm going to model this treatment effect process in 3 ways. So in one, there's only one treatment period. So this is going to be kind of like what I was saying. This was similar to the Card-Kruger paper. There's just one time in which one of the groups is treated and the other 2 are going to stay constant. And it's just going to be a constant level shift, like Nathan pointed out. So it's not going to be a trend shift. In the second simulation, what we're going to do is we're going to allow for staggered treatment timing, but with constant additive effect. So this will look like the graph from the Goodman and Bacon paper. So what I'm going to do is I'm going to simulate treatment effects. They're all positive in expectation. Again, just allowing a little bit of randomness here, but they're going to decrease over time. So the firms that get treated first are going to get it. Sorry, this for some reason I must have messed up the LaTeX here. For some reason, the treatment for the groups that are treated, incorporated in states that are treated in 1989, get a treatment effect of 5. The ones treated in the middle of the panel get a treatment effect of 3, and the ones treated at the end get a treatment effect of 1. Okay, so there's actually a lot of settings where economic theory would suggest that treatment effects are biggest for the earliest adopters. Just assume it's one of those settings, okay? And then what we're gonna do for the third one is allow for both staggered treatment timing and a change in trend effect. So these are what they call kind of dynamic treatment effects. So instead of a constant tau for each group, what I'm going to do is for each firm in a state, I'm going to pull a tau from normal distributions, again, that are centered at 0.5, 0.3, and 0.1. And what this is going to do is every year post-treatment, we're going to add that to it. So it's going to be more of a trend shift than it is going to be like a one-time level shift. And so this is what I was saying. So this is the kind of, it's easier to visualize this. So in the first one, right, we're going to have essentially 2 groups. One group gets a treatment in 1998. The other firms do not. And there's these kind of, random year effects that make things not perfectly linear, but, it's just a one-time shift between the treatment and the control states. The second one is where the treatment assignment is staggered, but it's still just this level shift. And then the third example is where kind of everything bad for this for this study design could happen, where we have treatment is staggered over time, and it doesn't get washed out in one period with the fixed effects. So it's going to change the trend. Does everybody kind of see what I'm doing here with these three simulations? Anyone have a question about this?
Just to clarify, the trend is different also in the two treated in the last simulation.
Sorry, say that one more time.
The trend is different in the two treated units in the last simulation.
Yeah, so what I was saying was so for this one, the second one, the earliest treated units get the largest treatment effect. So you'll see this red jump is much bigger than the blue jump and then the green jump that they get at the very end. And same for this one. What it does is there's going to be three different tau i's, right? So it's 0.5, 0.3, and 0.1 for the treatment group. So there's still the early treated group gets a higher trend shift than the later treated units. What this is going to do is just honestly just make it worse. So you could alternate it, because what you're doing is you're going to be using this one as a control for these two. And because this one has a higher treatment effect trend, what you're going to be doing is you're going to be subtracting out a large number. Right, that's all it is. But again, you can, I'm happy to actually share this if anybody uses R and wants to kind of, I find the simulations for me to just be kind of make it easy to understand where the stuff arises. I mean, there's always going to be a bias, but you know, how much there is a function of some of these parameters that I put in the data. So then what I'm going to do is with these simulated data sets, I'm going to run just the simple two-way fixed effects estimator that everybody runs, right? So after treatment, I'm going to include a binary indicator variable that's going to be 1 in the treated unit states, or so firms that are located in states post-treatment. It's going to be a 1. It's going to be a 0 otherwise. We're going to include firm and state level fixed effects, going to cluster the standard errors at the state level where treatment assignment happens, although that doesn't actually really matter in the setup. This is just kind of, again, the kind of what you see when you see a two-way fixed effects difference in difference model. For each of these data sets, I run a Monte Carlo simulation. So all that means is that I'm just going to re-simulate this data 1,000 times. And then I'm going to plot this distribution of delta DD. And then the bias is going to be the deviation from the true underlying treatment effect. I mean, I know exactly what the treatment effect is here because I increased this, all of these units by a simulated amount. And this is what we see, right? So there's no bias in that first example. There's no staggering, and there's kind of just level treatment effects. So here, there's no risk of a prior treated unit being used as a control for the future treated units. So what we see, these red lines, is the true treatment effect. And we see that our estimates are centered around the true treatment effect. In the second simulation, now if you'll remember, what this is there's staggered, but it's just a level shift, okay? So it's pretty close on like if you look at the actual numbers from, the true estimate was something around 3.02, and we're at 3.0. No, sorry, the true estimate was 3.04, and we're closer to 3.02. It's not a huge difference. And this was simply because of the weighting. Like we said, that it doesn't give each of these treated units equal weight. And so even though on average this treatment effect was a little more than 3, it's going to be a little bit lower than that because of where, the weights that the different groups are given based on how long they're treated within the sample. So that's the first kind of bias. And like I said earlier, that bias tends to not be huge. I mean, it's something we should be aware of. It might be the case in some settings. But like averaging over those weights, it's unless you have something that's like a U or an inverse U, I can't really see it mattering too much. The third simulation again, so this is the true treatment effect is over here. This is at 0. So not only is it not centered at the treatment effect, but actually it's of the opposite sign, and it would be statistically significant in the regression. Okay. So what this is because the early treated units are used as controls for the future treated units. The year fixed effects and the unit fixed effects are not picking up all of the change that happens from the treatment because the treatment is dynamic. And so that bias is flowing right into that two-way fixed effects estimate, and it's giving you the opposite sign because the treatment effects were largest in the beginning of the sample.
Andrew, I think if you put covariates, you get things even worse. So like,
I think that's true too. Yeah.
So and the philosophy of a diff and diff is that you want to throw in as many covariates as you want, like to show that you're controlling for lots of stuff.
Yeah.
But that so many covariates are going to change the weighting so much that you get even more shifting. So
yeah, I mean, I'll say like the theoretical papers that I use later on this, they don't even allow for time varying covariates, because like the theory for that is actually quite hard to write down. And we've known that since like a Viscusi paper in the 80s that, when you have these different groups over time, the covariates, it's actually quite challenging. I'm with you on that. Another thing that I see a lot that becomes very hard for me is like 4 or 5 levels of fixed effects with a difference in difference framework on top of it. Again, like fundamentally what we want a difference of difference to be is a comparison of different groups means. Like that's what it is. And it becomes very, very hard to understand after you've done all that, what the comparison of means is, besides writing down and saying, I'm controlling for industry and year and time and whatever fixed effects, kind of, actually explaining to somebody what those comparisons of means are, it just becomes very hard. And so I'm with you that I think the covariates, this is a simple one with no covariates. The covariates makes it more confusing, but unlikely to make it better in my opinion as well.
Yeah.
Does anybody else have a question just before we move on of kind of like, those were the 3 data generating processes. This is the result you get if you just do the kind of standard textbook 2-way fixed effects, difference and difference, based on that data set. All right, then I'll move on. So one thing that's nice that the Goodman-Bacon paper has that I really like to use, I'm using in one of my papers now, is what you can do is you can decompose the treatment effects into these 2 groups. So, right, early versus later treated units are not necessarily biased unless there's like anticipation or something in the pre-trends that kind of messes up the estimate. And not just pre-trends, but anticipation. So if the units know that they're going to be treated and adjust their behavior, then everything becomes more challenging. If you assume that's not the case, then you can use later treated units as a control for early treated units because they have not yet been treated yet, so we don't have that bias. But the later versus the early treated units, those are the ones that have bias, right? Because if there's any of these trends, you're subtracting out kind of these firms, you're subtracting out that treatment effect, and you're going to get something that's either attenuated towards 0 or so attenuated that it's of the opposite sign. And what you can do is you can just kind of break down. So these are the different 2x2. So we had 3 groups here. We're going to end up having 6 different comparisons. And what you can see is like it's positive and what we'd expect, centered somewhere around 3 for the ones that are unbiased, but it's negative for the later versus the earlier treated units, which weirdly have a little bit more weight here. So what's nice about this, I like to do, is that if you have a paper and you want to understand what is driving that overall weighted average estimate, this decomposition kind of allows you to like do it in a somewhat parsimonious way of just being like, okay, so these ones we think might have issues. These ones are all of opposite signs of these ones. That's a reason to be concerned. They've got this both in Stata and in R now. It doesn't allow for covariates because it doesn't really matter, but it's hard to actually say, what those comparisons of means are once you throw in the covariates and you use the Frisch-Wall-Lovell. It's hard to like know what you're comparing, but you can just do it without covariates and see kind of between these different groups, how does the supposed treatment effect change. Now I'm just going to go through a few methods that have been developed within the last few years that people have done that get around some of these issues. So this one I really like a lot. It's from Callaway and Santa Ana. It doesn't use a regression approach or a linear regression approach. Instead, what it does is it uses inverse propensity weighted long differences in the cohort average treatment effect. And so, it's a lot of, letters here, and that sentence that I wrote doesn't really do them justice. It's just a way of saying, like, if something's treated in 2008, find units that are treated in before, that are not treated yet, and just take the long difference between those units, right? That's all kind of we're trying to do anyways. And the nice thing is that if you want to use covariates in their model, they don't have it with time varying covariates, again, because it becomes complicated, although I know they're thinking about it and working on it. But, if you want there to be differences between the units that are stationary differences, so states might have underlying, differences in some variable, you can just kind of use this propensity score inverse weighted models, which has this nice feature. They also have a doubly robust version, which is nice. where you kind of get two cracks at the apple. But it's just kind of, once you figure out what it's doing, it's quite simple. All you're doing is comparing means between groups. The doubly robust version will upweight firms that look most like the treated units and downweight ones that don't. But at the end of the day, it's just this long difference of kind of comparing the means between those two. The second model is this one called, I believe it's actually Son and Abraham, not Abraham and Son. I need to fix these slides. All this does is do an event study approach like we talked about, but instead of just having like indicator variables for -1, -2, it has those, but they're interacted with what year that unit was treated. So we treat all these things as kind of cohorts. So everything that's treated in 1998 gets treated similarly. You're gonna end up taking the average of them. And as long as you saturate those fixed effects so that you have one for each relative year treatment group cohort combination, then this issue that we've talked about, which is prior treated units being used as controls for future treated units, won't actually happen. It's just the algebra of how OLS does that. So, you know, they don't really have a way to use covariates with this, although honestly, I think if you can use covariates, or we think we can use covariates in a regular staggered difference in difference design, I don't see any reason why whatever ostensible theory we had to do that before would not flow through with the saturated fixed effects. But anyways, all you do is you do that, and then what you'll have is you'll have a bunch of relative time indicators for each cohort, and then you just need to take the weighted average of those based on how many firms, like what percentage of the treated firms at year T-1 come from each of the cohorts, right? So you just kind of use a linear combination approach for that. What's important to know about this approach that I personally don't love is that the only control units are going to be firms that are never treated, or units that are never treated within your panel. So say you have a panel where, like, by the end of it, 2% are untreated and everybody else is treated. The controls that you use there are only going to be that 2%. And so, you know, it's perhaps not the most efficient estimator in that approach, whereas some of these other ones allow you to kind of increase the sample of control units. And then the last approach is what I just call stacked regression. A lot of papers kind of use this. It's similar to the standard two-way fixed effects, but what it does is just kind of be explicitly clear about the sample construction so that no previously treated units can enter as controls. And it does this just by trimming the sample. So what you do is for each treatment cohort, you create a separate data set. And what that does is have all the units that are treated in that year. And then if you want to, say you want to do an event study where you look from 5 years prior to 5 years post, right? Then here would be, this would be G plus K, K would be 5. So what you do is you take all the firms that are treated in that year, and then you take all firms that are not treated by that year plus 5. So if the firms that you're looking at were treated in 2000, you know, potential control units could be anything that's treated in 2006 or afterwards, and anything that's never treated, okay? Then you're just gonna keep those years from -5 to 5. You're gonna drop everything else, you know, so then you'll have a cohort specific data set, and then you're just gonna stack those on top of each other, okay? And so now it's centered in relative time instead of in calendar time. And what that does is get rid of that kind of minor issue, which is the weird weighting where you're upweighting things treated in the middle or the beginning or the end, because everything's now treated in the middle. They're all going to get the same weight. And then you just run the fixed effects on the stacked regression. The only thing is that you need to interact the fixed effects with an indicator for which treatment data set it is, so that you're actually getting those means done correctly. Okay, so does everybody kind of, I mean, I know I kind of rushed through these 3 methods, but, you know, I'm happy to, if anybody wants to send me an email, or I can send you guys code. You know, I don't think it makes sense to kind of go through these super exhaustively. The main point is just that all 3 of these focus on this one, on the issue, which is that you don't want to use units that were treated in the prior period as controls for units that are treated in the future period. But does anybody have any specific questions about any of these, so I don't kind of lose everyone?
So I did have one question.
Yeah.
So why not just use regression kink design combined with diff and diff?
Why not use, sorry, regression discontinuity design? Is that what you said?
Oh, kink, regression kink. You know,
yeah.
I mean,
yeah.
That seems to be much more efficient than any of these methods.
I need to think a little bit more about it. As a non-public econ person, I actually don't really use kink designs or see them used in my field all that often. but it's possible that could be a more efficient way to do this. I still think you have to think about, because here it's about the time component rather than a lot of the kink designs you see are about some threshold. Like in terms of like, you think that there's some kink at some function of the distribution, whereas here the issue is that over time things that get treated versus untreated, you're comparing them against each other. How you would incorporate the kink, it's something I'll talk to the people that I'm working on this with. Maybe there's, like it's not a bad idea. I'm just kind of struggling to think about exactly how you would do it, but that could be a way. I mean, I think I'm always better. Like, I think it's good to put a little more structure on what you think the relationship is. If you think it's a kink, I mean, obviously with the simulated data, I simulated a kink, right? So,
right, yeah.
Like I think actually the better way to simulate this data, I've thought about changing it, is to make it like a log function, right? Because it's like, now it's like, I'm really kind of tipping the scales a little bit because something continues in perpetuity. Whereas in reality, if you look at an event study plot in most papers, it's kind of like, it just takes a little time, but then it eventually levels off. And I think I should probably change the simulations to kind of look more like that. But I've just always been too lazy to go back to the code and do that. But it's a good point. Does anybody else have a question before I move on?
Andrew, just a heads up, you have about 12 minutes. Okay. And yeah, so if you want to take questions at the end, that's also okay with us.
Okay, sounds good. Thank you.
No worries.
So all this shows is with that same simulated data set where everything was very not good. So this is just simulation 3. So the one where we really kind of created a bunch of the issues. All of these approaches uncover this true treatment effect. The true effect is the blue line, these red dots. It's just kind of, and this is an event study approach, which all of these models, one thing moving forward is that this, the issue becomes much more pronounced when you use the binary indicator variable approach, and that we should really all be kind of estimating these things in relative time. And then if you want one number for what your treatment effect is, you can just kind of take the linear combination of these post-treatment indicator variables. Conditional on being satisfied that there's a lack of pre-trends. On top of that, there's a really good paper that was John Roth's job market paper this year about how to also kind of not just throw out things where you think there's bad pre-trends, that actually we should be kind of taking a Mansky bound approach here, which I think is right. I think it's going to take a little while maybe for people to start doing that, but to say there might be differences between your treated and control units with a difference in difference, and you can still say something about, within bounds, what do we think the change in the trends was. But anyways, all this is to show, simulate some data, show it's quite easy actually to make these estimates kind of flawed if you have time varying treatment effects, but that all 3 of these methods seem to get across it. It's obviously a stylized data generating process. Sometimes using real data, these things will give you different results, and it's kind of unclear. Ex ante maybe which one you want, but at least in this approach that they all work. All right, so I have 10 minutes. I actually went through all this today, and we've updated these things. It's actually not the greatest example of this issue anymore, now that I've kind of fixed some of the stuff. But I'll still show you about, like, this is how I think about doing difference and difference now. I have, like I said, a paper hopefully coming out with like what I think is a very good example of where this thing can really matter. But in this example, I just thought it was an interesting public example that came out where people are looking at the staggered adoption of medical marijuana laws in the United States and what effect that has on opioid overdose deaths. So a paper came out in 2014, I think it was in JAMA or something, and it used a staggered difference in difference design, and it found that states that passed medical marijuana laws experienced a slower increase in opioid overdose mortality using a sample of data from 1999 to 2010. Then a paper came out this year, the beginning of this year, and what they did was they just extended the data from 2010 to 2017. And in this period, an extra 32 states passed medical marijuana laws. Not only did the results go away, but the sign flips. So now medical marijuana laws are actually associated with higher opioid overdose deaths. And so while neither of these papers actually kind of say that what they're doing is a difference in difference, they're using a two-way fixed effects regression with a binary indicator variable. So, it's effectively a difference in difference. And the question is, to what extent is there really a relationship here? And could it be the case that in this latter period where so many states have adapted it, maybe there's not actually higher opioid overdose deaths, but it's just that you're comparing to states that previously passed, and those states had a difference in trends. So briefly, I just kind of like replicated. The nice thing is the data was presented with the journal. I'm getting fairly close to what the published estimates were of these two papers. So the first thing is, they don't present the event study results, but I always think it's good to kind of try to see what's going on. So there was little evidence for me kind of using the data that the covariates mattered in these regressions at all. They didn't change the coefficients at all. Most of them were insignificant. So, for the purpose of this replication, I just dropped all the covariates. And so we're just going to estimate a standard difference in difference. One thing that's important here, and I found this matters actually quite a lot in real papers, is like, how many indicators do you include? It's kind of just like a practical question of like when you run event study difference in differences. And I think usually what you see is people will include, so say you wanted to look from -5 to 5, they'll include indicators for relative years -5 to 5 and leave out t-1 or t=0. And then they'll just like not do anything with the before -5s and the after +5s. And what that actually does is it changes what you're comparing against, and it can actually have a really big effect. So I have another post where I kind of simulate data and show what you really need to do. In other papers, what they'll do is they'll bin. So they'll include one for everything less than -5 and everything greater than +5. That also still creates these issues. And, for reasons that I'm not perfectly aware of, to be honest, why, I think it just, OLS does weird weighting stuff and it kind of messes with these comparisons. So what I think you really need to do from talking with people and simulating data is you need to include all of the relative time indicators that are in your data. So find the most negative relative year, the most positive relative year. When you have a staggered design, you actually need to leave out 2 years. And this was found in a paper. So I always leave out the most negative relative indicator and the one for t-1. And you don't need to like present all of them if you're doing an event study plot, but you actually need to estimate those individually. And what you see is that, if you do this event study approach, this was the first paper's results that stopped in 2010. They do have, a negative effect, although, it's kind of drawn by this weird discontinuous jump that occurred at the year -1, which might suggest that maybe there was, like the treatment was endogenous to increases in the mortality rate. I mean, or it's just spurious, who knows. And then if you pull it out to 2017, you see that there is this kind of positive treatment effect, or what appears to be a positive treatment effect. So this is all still just OLS, not correcting for any of these issues, but kind of fully saturating the time indicators. And again, what you can do with this Goodman-Bacon decomposition is see if when you do those binary indicator regressions, what's driving the result. So if you remember, the earlier versus later treated, these ones are good, these ones are bad, these ones are good, right? So previously they found negative in the sample, and it was positive for the bad, kind of the troubling sample. In the later estimates, similarly, they find this is kind of a little weird. So the overall positive effect is driven by a negative effect within the sample for earlier versus later treated. A positive effect, this is, again, the problem grouping is positive, which is driving the positive effect partially. But then the treated versus untreated is also positive, although it's, you can see the total weights that these all contribute. Anyways, just to say, there could be an issue in this later sample based on the fact that we have this positive effect that's feeding into, it's the largest weight, and it's feeding into the later versus earlier treated units. So again, it's just, I think this is a good diagnostic tool that Andrew came up with to kind of try to see like what's kind of coming into this overall average. And then finally, if you kind of do these what I call remedies here. So Abraham and Son, so the top row here will be the data that stopped in 2010, and the bottom row here will be the data when we extend it all the way to 2017. And what we see is, again, still pretty much the same the same relationships here as the full event study. So not totally positive why. I think it's because there is a decent amount of never treated units in this data versus some of the examples I have where everything is treated and you really do see this stuff flip. But, you know, I think this is the way going forward that we should be thinking, in my opinion, about doing difference in difference designs is, you know, probably trying different methods and just making sure that they're all robust to this critique. All right, because I have like pretty much no time left, just going to end saying difference in difference, they're a powerful tool. We're all going to keep using them, but we should make sure that we understand what we're doing here. It's a comparison of means. And I think at a minimum, we should kind of understand what means we're comparing and whether or not those means actually make sense. There's multiple new methods. They all kind of ensure that what you're doing is not using prior units, treated units as controls. I think you should probably tailor the selection of the method to the way your data looks. Like I said, with the Abraham-Sun method, or Sun-Abraham method, you know, it's only using never treated units as controls. I think you should kind of look at your data. If that group is going to be very, very small, then maybe it makes sense to use a stacked regression approach, which allows you to have kind of more data and more controls. As to the, you know, replication example, unclear what's going on in medical marijuana laws and opioid mortality rates. Very unlikely, you know, well, previously these results changed a little bit more, but, you know, once you add the new firms, it's probably unlikely with a full sample that, you know, that the results from the first paper were robust. But anyways, I'll end there. You know, if anybody has any questions, happy to take them. Or if you guys can always shoot me emails, and, you know, I'm happy to think through this stuff with everybody and the work you guys are doing.
Excellent. Thank you, Andrew. Do you have time for a few questions?
I have more. Yeah, I'm totally free. So happy to take questions from anybody.
Perfect. Okay, audience. Any questions?
Hey, Andrew, I had a question.
Yeah.
With the stacked regression, like,
Hi, I do have a question.
How do you
Can you hear me?
How do you think of? Oh, sorry. How do you think about the case where, like, there might be different size treatment cohorts, and sort of how OLS is gonna, like, average those treatment effects?
Yeah, no, that's a good point. I mean, I think if you read Andrew's paper, which I think he has an update on MBR now, he kind of goes into that weighting. I mean, it will give larger groups higher weight with OLS in that treatment effect estimation. I know there's another paper out that I actually need to read that I just saw, not about difference in difference, but about two-way fixed effects regressions in general, and that smaller groups get higher weights. That I think just came out in Restat. I need to figure out how those two facts can be true at the same time. But yeah, you know, the different group sizes will go into the weighting with the stacked approach because OLS will upweight the larger units, I believe, unless everything is backwards now. Whereas the Abraham-Sun approach, or Sun-Abraham, and Pedro's approach are quite explicit about just weighting directly by the size of the groupings. Whereas, you know, the variance, you know, it's going to be if you do OLS, it's going to be somewhere on the, you know, on the frontier of the bias variance trade-off, just by the way that OLS is going to weight those things. But yeah, no, it's a good point. I mean, you can always, you know, if you care more about that too, you can, with all these pros, you could always do weighted OLS too, where you're going to upweight the actual coefficients that go in based on the size of your units. I know Pedro has in his code, which is just called DID. It's on Crayon. Has a weight option if you want to put in weights as well.
We have Sasha next, and then Pom.
Yeah, one question about treatments that have an event nature. So sometimes, say, a president gets assassinated, is an event that may then have effect. So the treatment is switched on and then off again.
Yeah.
That also is often done by people in a different diff setting.
Yeah.
And an issue that also then comes in, whether you have an initial conditions problem. Something may have just happened before your panel starts.
Yeah.
So a unit is latently treated, but you don't know.
Yeah. Yeah. No, I mean, that's true. I mean, for your second point, again, I think that's usually why the event study approach, I find preferable in general, because, you know, to the extent that you see like consistent timing differences between, right, to the extent you see, if you do it and you see that the whole treatment effect comes in the year before, right, then you can kind of at least come up with a story for why you think the timing occurs in that manner. The first point as to treatment indicators that turn on and off and on and off is actually much harder. So most all of these methods that I've described to you assume that once you get treated, you stay treated for the balance of your panel, because the algebra becomes difficult. Again, I'm not a econometric theorist by any stretch of the imagination, but I know it becomes actually quite hard to do that. I usually think of the models where you have something that's like on and off like that. I usually like the kind of biostat type models, like mean nested models or mean structural models, because they're actually kind of explicitly modeling that treatment assignment decision. So you can think of like, they're usually looking at like dose responses. So like, why does a doctor decide to give this pill? They might go on and off the medication. And, you know, like James Robbins and all those guys are super, super bright, even though us economists don't like to read them as much as we should. And they've thought about kind of the way in which you model the relationship between the outcome variable and the treatment assignment decision. And if you think that there's a kind of feedback mechanism between those two, you really need to model that. Now, I've actually tried to use some of those models in my work, and if your thing doesn't turn back on, like you need a constant like propensity score that feeds into that. And if your thing is like I look at hedge fund activism for some of my research, and we kind of just assume, we don't know when it turns off. We assume it has a shelf life, that it matters to managers for 0 to 5 years. And it's like, it's very hard to use those models then. But if you have something that really is like patents or something that's turning on and off quite frequently, I think personally those models are more intuitive than like just fitting a difference in difference on something that's turning on and turning off. Because those mean comparisons, like we've talked about with the groups, whether or not it's a treatment or control, gets super fuzzy with difference in difference if you're not assuming that something's constantly treated afterwards.
Thank you. Thanks.
Yeah, you're welcome.
Hi, Andrew. Thanks for a very helpful talk. So my question is about this issue that you briefly mentioned about how to, I think, include the period, say, before -5. And if I understand correctly, you're saying that if you include just a dummy for like, say, -6 and before.
Yeah.
And 5+ and after, are you saying that's still not, still having bias? Can you explain the intuition there and point us to the paper that you said is talking about this?
Yeah, no. Oh, so the paper that says that I talked about, what that paper showed was that if you're doing, say you're doing a difference in difference with no staggering, right? And you because of OLS and you have unit fixed effects, like you need to leave out one time period, right? That becomes the reference time period. This paper showed that when you have staggered, you actually need to leave out 2. And it's, I'll send it to, it's Haravel and Barusiak. It's still a working paper. I don't know if they're planning to publish it, but it's a very good paper about event study difference in difference that came out like 2017. And it's just available if you just Google it. Here, I'll send it.
Thank you.
Yeah. And so that's not necessarily about having to fully saturate. That's about having to leave out 2 time periods. The binning is just like Andrew and I, Goodman Bacon and I have been kind of thinking about this. And I have, if you Google me, Andrew Baker, Stanford, you go to my website, I have like a little post on there, so like how to create relative time indicators. And so I simulated data to show that, like, because like, you know, do you just leave if you have a pre-indicator, it's still gonna essentially kind of capture, it's gonna have these same issues that we've been talking about, and that, you know, you really need to pretty much Pedro's method kind of, and Abraham's son do all of the relative time indicators. So I started thinking like, okay, well, sometimes when we do the OLS, we just bin, and sometimes we, you know, these other people are fitting all of them. Which one of these like actually do better with the data? Like if you just kind of simulate some data, regular data generating process. And in just some papers that I've been replicating for this work, I've found that just doing that one thing, changing from either not having any bins or going from binning to fully letting out these indicators, it can have a huge effect. Not huge, but like it really does change the reference coefficients there. So it's just something to think about. But I don't know if there's any papers that have actually like developed that theory. I think everybody kind of just ad hoc runs their regressions. But I do think that these type of things, like as a community of scholars, like we should get together and like, you know, like not make everybody derive from first principles how they're gonna like set up a regression. It seems like the way we do this, and I like try to put the stuff on my website and do whatever and talk to people and get them to write stuff up, because I think it's just helpful so that we're all like can kind of focus on the research that we care about and not have to like, you know, spend so much time worrying that we're messing things up like I do, like I worry about. So, but yeah, hopefully that's somewhat helpful.
Thanks. Yeah, if you can put down the name of the paper that you just mentioned,
Yeah,
that would be great. I didn't quite catch how to spell it.
Let me.
Thank you.
See.
Or later, I can drop you an email too. But thank you.
Here's chat here. I think it's 2017. But if you just Google those two names, then it'll come up and it says like event study designs or something like that.
Thanks.
You're welcome.
Okay, so there's one more question in the chat from Fabio Martinenghi. Hi, Andrew, you briefly mentioned stacked regression and how some people use it to avoid using the already treated to build the counterfactual. Is there any econometric paper on this? And then David already posted the Senghis-Dubé Sipera QJ paper, but do you know any others?
Yeah, so that is actually something I talked about. I like the stacked approach personally, because I think it's just kind of intuitive and it's not moving outside of what, personally, I really like Pedro's paper the most. Like if we're just being honest about these different approaches, I think to me it's the most intuitive, but you have to fit propensity scores, and like a lot of economists don't like the idea of a propensity score. And so the stacked approach is literally the same regression that you're already running. You're just kind of changing the data. Having said that, I don't think that any papers, to my knowledge, when I've asked around, have actually derived this. So the Dubé paper I really like. There's it's in an appendix where he does this. But you know, he is like us, or like me, like an applied economist. I think, you know, there are other economics papers that do this. There's this other one. I can find it, that was in an AEJ a couple years ago that was really good, that also used it. But, you know, I don't think anyone's like derived the asymptotics of these models, which I think would be the beneficial approach. I mean, I don't think I have the slide anymore where I said that's kind of one of the downsides of this model, is that it hasn't been like, at least to the best of my knowledge, kind of proven by the like smart, you know, econometric theorists that this is like a totally valid approach, that the standard errors are perfectly normal, and, you know, but you know, to a certain extent, I think it's kind of clear what the model does. It works on simulated data. I'm kind of okay with it. But you know, if there is a paper and someone finds it, it'd be great if you email me, because I would add it to kind of my paper and slides on this. But yeah, I think it's kind of something people have realized what this weighting issue is and kind of come up with this hack around it. But I don't think it's been like proven to work.
Okay, cool. Thank you, Andrew.
Yeah.
I think there's one more question, raised hand, if that's okay.
Yes.
Yeah, I'm totally good. So
yeah. Yes. Hi, Andrew. Thanks for the talk. It's very interesting. So I was wondering if we should also run event time stuff based on waves. So if part of the problem with this two-way fixed effect is that I guess different treatment groups have different effects. Then with event time, we also have the same problem. Considering, like, for example, later treated waves may contribute more to estimating the pre-trend, and like earlier treated wave can contribute more to estimating the post-treatment effects. If you put everything in one event time, it can like different compositions. So should we also break it down by waves?
That's a really good point. I mean, one nice attribute of both the Sun-Abraham approach and the Callaway-Santa Ana approach is that they actually spit out, well, the Sun-Abraham approach, you have to estimate yourself. But, you know, what you do is you estimate those by treatment cohort, and then you take the combination of them across groups at the relative time level. Now, you can just plot all of those the group level event studies as well, right? And Pedro's code actually spits out the group, they call them like ATT GT. So the average treatment effect on the treated, GT is like group time, right? So
Right.
-2 for this group. And I actually think you're totally right that we should present all of those different waves, because especially like a lot of the things that I study, what happened in the 80s and what happened in the 2000s are quite different. And that's like variation that we should be interested in, right? So above and beyond how it's being used to identify, it's just like, we throw everything together into one coefficient, but it's covering up a lot of heterogeneity. And so I think you're totally right. I think it's an advantage of some of these new approaches is there could be an interesting story there as well, in terms of how this thing changed with treatment cohorts.
Yeah, for sure. Yeah, I thought the same criticisms or same problem may apply over if we're doing it, we will break it down by groups more for to different difficulty. We may suit it for event time.
Yeah.
Thank you.
You're welcome.
Cool. All right. Thank you very much, Paul. So there's a question, Andrew. Are you happy to share the slides as well?
Yeah, I was just gonna say they're on my. Well, I was gonna type it. So they're on my website again. So my website is Andrew. I'll put it in here at netlify.com. Let me send it to everyone. If you want the actual code to it, I'll put my email on here just because I don't really know everyone's. But if anybody wants the actual like script that makes these slides, and not just the slides, because I have the code in there too. If you want to know like how I make the dummy variables or whatever, I'm happy to share that as well. This is all kind of open source stuff. So I just sent my email to the group chat. So anybody who wants to email me about anything about what I talked about or just anything, like feel free to email me. I like meeting new people. You Aussies are all quite nice. But also the slides themselves are just on my website. So if all you care about is to kind of refer to this, you can find them on the website.
Fantastic. Well, I mean, that's a great public good to the community. Would be good to see more of that. So look, Andrew, I think that was a fantastic talk. I mean, I learned a lot, and I think I speak for others. I mean, very great presentation. And by the way, you are the new record holder in terms of attendance. We broke officially the 100 participant mark. So
not on my CV.
Exactly. We will send you the medal. So yeah, no, that was amazing. And as I said before, if in better times, hopefully in the near future, if you manage to come to the region, just let us know. And normally what we do is, when people manage to come over, we will spread the word, and then they get, can tour around Australia if there's sufficient demand. So that's great.
I would love to. I'd love to come out, and like I said, I've never been to Australia. Hopefully, I don't even think we're allowed to travel to anything. I think there's only like 2 countries in the whole world that us Americans are allowed to travel to right now. So hopefully it could happen sometime. Before we turn into Gilead.
Cool. Yeah.